Okay, so when it comes to finite elements, spatially, we describe what M and K is doing. So that's our shape functions, and that tells us sort of how things lump to nodes. We've got degrees of freedom that describe what's going on. When it comes to the time side, we are solving that as a differential equation. So you can see this is a second order differential equation, and so essentially we're going to have two initial conditions to be able to solve this. An initial condition for velocity and an initial condition for displacement. The same as what you've done in dynamics in the second year. This is really what this boils down to. This is a free vibration problem because there's no loading, there's no forcing of this. And so this is really a system with no damping either. So this thing will go on forever. In this, if you have initial condition that ensures that there is either some strain energy or some kinetic energy in the system, things will then switch. The energy will switch between the strain and the kinetic energy up and until at infinitum. Okay, so that's important to understand that from the response. Okay, but there are really two classes, big classes to solve this. The one is the modal approaches, and that they allow you to really efficiently express a solution, so that I can tell you what is the solution after a million seconds without having to start at 0 seconds. I can really just tell you evaluate these expressions after a million seconds, because essentially what we're doing is we're splitting sort of the time contribution into sort of a analytical form, and we sort of have the modal contribution for each of those modes. So with the modal approaches, we really say, let's take the system, break it into lots of eigenvectors. We have the eigenvalues, we understand what they mean. They are the vibration frequencies, circular frequencies for vibration. The modes are the deformation shapes that we have. And so I can then say, if you can combine those, do a summation of them for lots of modes, for instance, so some of the modes, and then I have an analytical expression as a kind of a sinusoidal kind of solution of how things would vary as a function of time. I just have a couple of coefficients that I need to solve for to be able to do that, but then at least I can get going on that problem. And so as an example that I'm going to show you is the underdamped free vibration problem, so that you can relate this back to what you've done in vibrations. But the reality is I've got eigenvectors, the u's here, I've got the eigenvalues, the omega j's there. I can sum over all the modes from j from 1 to n. I have these unknown CJs and DJs that I need to solve for. You can see the C is nice and linear in terms of this, but the DJs are inside the sine wave, so sine expression, so that's non-linear. So that's one way to try and factor what's going on. But I can then say this is a general solution to this eigenvalue problem that we have here. So I can then say this is my displacement solution. So if I know what CJ and DJ is, I can tell you after a million seconds what is the response. This is beautiful. I can also differentiate this and tell you what's the velocity. This is what we've done here. So this is really what it boils down to. How do I solve for CJs and for DJs? Well, I need to solve it from the initial conditions of my problem. So what is the velocity and what is the displacement at time 0? So this is what this boils down to. If I evaluate time 0 these expressions for displacement and the velocity, I essentially get down this. So I'm left with a DJ here because that's 0. Same for the cosine, for the cosine term, and for the sine term, the same story. The DJ there. I've got the CJ here, but now with the velocity, I've got an omega that pops out if I do the differentiation. That gives me sort of the CJW, or the omega J. That's what I've got here. This is just the eigenvector, okay? And this is just essentially the square root of the eigenvalue. That's what we have there. And the beauty is this system is usually very much overdetermined. So this is related to the number of degrees of freedom that I have, okay? The U's, so that could be a million degrees of freedom that I have. The N's here are related to the number of modes that I choose. If I choose 5 modes, I've got 10 things I have to solve for CJ and for DJ. If I choose 4, I've got 8 of them that I have to solve for. So I've got freedom of 8 variables to try and satisfy a million equations. So that's a least squares solution that you need to do there. Okay, it's an overdetermined system of equations. Least squares is what you need to do to solve this system. Okay, but once we've solved for CJ and for DJ from the initial conditions, so this is something you would know. What is my initial condition? What's my initial condition for velocity? Then I can solve for CJ and for DJ because I express it then essentially as the number of modes times the number of C's and D's. Okay, the disadvantage of this is it's nonlinear in D. And so I can try to solve it with different variables here, but I still have to enforce some equality constraints between those variables. Alternatively, I can say let's get a formulation where I express it this summation as u as a j cosine plus bj sine. So I've got the a's and I've got the b's that I can express essentially this nodal displacement of. I can then differentiate that to get the velocities out, but the advantage is it's linear in alpha and it's linear in b. That's what it boils down to. Okay, same, just a different form, but same story. I can then go through this process and solve for those initial conditions, and that's it. This is one way of solving it. It's highly efficient, economical. You can evaluate at any time what's chopping. Okay, that is really important to understand. The other thought of school, the other approach, is what's called the direct integration. Where is this? Direct integration. And here, under direct integration, there's again two small philosophies. The one is called explicit integration, and the other one is called implicit integration. And what we are solving here is just stock standard differential equation, okay, in time. Lots of variables, lots of nodal variables, but we're just updating. So I've got a vector of u's of my displacement, nodal displacement at the next time step as a function. If it's only a function of all the displacements, velocity, accelerations of the previous time steps, it can be just immediately the previous or even more in the past. But if it's purely a function of stuff in the past, the next time, the step, next time at n plus 1, which is the time step, let's call it n plus 1, is a function of only time stuff and time step n and backwards. That is called explicit integration. So when I do my differential equation, and that's really where finite differences will come into play. That's the stuff that you've done in your second year when you did sort of differential equations, numerical integration thereof. Okay, I can also have another scheme which is called essentially the implicit integration, where the displacement into the future at n plus 1 not only depends on stuff at n and backwards, but also on the velocities at n plus 1 and the accelerations at n plus 1. That's an important consideration. Okay, so this is important to understand that this is now what implicit implies. Can you see the difference here? There's nothing here is n plus 1, but here we have two terms that are n plus 1, so the displacement is a function of velocities and accelerations also at the next time step. Okay, and so we can generalize this, solving these two types of schemes in a single framework, which is very popular in finite elements. It's called the generalized Newmark algorithm, GN22. It's got parameters beta 1 and beta 2 I can choose, and by the choice I make there, I will have implicit or explicit schemes. Okay, so for instance, if you look at this first equation here, I've got u n plus 1. So that's a nodal displacement n plus 1. It's a function of the nodal displacements at time n, plus some delta t, the velocities at time n, plus a half, then 1 minus beta 2, accelerations at time n, and then plus a half beta 2 acceleration at times n plus 1. So immediately I can just tell you, if I choose beta 2 equals to 1, okay, then this term falls away. I'm sitting with an implicit scheme immediately, because I know that I'm using accelerations at n plus 1. If I choose beta 2 equals to 0, this falls away. This becomes the term that dominates there, and I can then tell you that I've got a u double dot n. So that's then an explicit in terms of this update of n plus 1. Do you see that? And so that's the beauty of what difference is between implicit and explicit. I can also choose beta half, for instance, or quarter, and then I derive lots of different other schemes. It's all based on this generalized Newmark algorithm, GN22. Okay, I can also express the velocities at n plus 1 using another parameter, beta 1, to say how much of the velocity acceleration at n plus 1 and n you want to use in the computation of the velocities, for instance. This is really what it boils down to. The difference with these direct integration schemes is we always start at time step 0. Okay, so if I want to apologies, let me just quickly cough. Let me see if I can make the all right, so I'm back on track. So if you want to know what is response at a million seconds, you have to integrate from 0 up to a million seconds. Okay, that is important to understand. So these things can be very costly if you need to know things very far into the future. And also, there's a big difference in the integration, explicit and implicit schemes, in terms of what is an acceptable delta t. And this is what we're going to explore next.